Assalamu alaikum, my dear cadets of class 12. Welcome to my online physics class. You are not able to stay at your second home due to corona outbreak. Don't go outside of your home. Please stay home, stay safe. Try to follow this coronavirus protection advice. Before starting my class, I would like to introduce myself. This is Mohammad Kamrujiman Khan, lecturer, Department of Physics, Borishal Cadet College. This class for class 12, subject physics, chapter 2, static electricity. You know it very well that this chapter is related about static electricity, and this is the example of static electricity. No more delay here. Since this is my continuation of my previous class, so today's topics are Gauss law and electric dipole. No more delay here, so I'm going to start my today's class. At first, Gauss law. Before starting Gauss law, I have to discuss about some parameters related to Gauss law. At first, equipotential surface. A surface at every point of which the potential is same is called equipotential surface. For the uniform electric field, the potential of this place V1, this is V2 and this is V3. Since this is the equipotential surface, so potential V1, V2 and V3 will be same. For an isolated charge, yes, you know it very well from the properties of a sphere of that must be here. The solid should be, the sphere should be solid. The sphere should be solid. You know it very well that the charge distribution on the surface of a solid is same to its any point inside the sphere. So this is also an example of equipotential surface. Spherical equipotential surface. This is the example of spherical equipotential surface. Now, properties of equipotential surface. Since the potential of any point is same, so there is no work done will be happen. The electric field is always perpendicular to the element BL of the equipotential surface. Since no work is done on equipotential surface, so work W is equal to A real cos of theta is equal to 0. Boys, let's see the characteristics of equipotential surface at a glance. Surface of a charged conductor is always equipotential surface. Electric charges on this surface remain stationary. Electric lines of force penetrate the equipotential surface at right angle. No work is done in transferring charge from one point to another point inside the equipotential surface. Surface or volume of a body can be equipotential surface. Again, surface and volume in space can be of equipotential surface. These are the main criteria of an equipotential surface. Boys, my next topic is area vector. A small area of a surface can be represented by a vector. Let us suppose this is our large area, but this portion is a small area and it is defined or symbolized by ds. Boys, it is defined or symbolized by ds. Okay, I'm talking about this surface. So let's see area vector. Since it is a vector, so it must have direction, and direction is perpendicular or normal to the surface of this small ds. Okay, ds vector is equal to ds is multiplied by area vector electric flux. Electric flux linked with an area is defined as the total number of electric lines of force. My dear boys, electric flux is the number of electric lines of force that are passing through a unit area or a area that are passing through a unit area or a area. Okay, and this line must be passed normally, not must be passed normally. Okay, this is the surface and these electric lines of force are passing along this way, and this is small area ds, and it is also, and the direction of this ds is deflected by an angle theta, so it is here 90 degree. It is parallel to the electric lines of force. So my dear boys, you know it very well about the electric flux. So I will not discuss elaborately here. Let's see equation phi is equal to E dot ds, that is E ds cos of theta. Okay, total flux phi over the whole surface S due to an electric field E. You know it very well that if you want to the total electric flux, you have to integrate this equation. Okay, so we are integrating this, and now we are getting phi is equal to E s cos of theta, E s cos of theta, E s cos of theta, and it is the scalar product. You know it very well. Electric flux is a scalar quantity, so but it is, or it has a property of vector field. It has a property of vector field. SI unit of flux is Newton meter square per coulomb or Joule meter per coulomb. Okay, boys, look at here. The unit of electric line of flux is equal to Newton meter square per coulomb or Joule meter per coulomb. Special cases, what will be the value of flux if the angle will be changed? Okay, for this case phi is positive, for this case phi is 0, and for this case phi is negative. Solid angle, my dear boys, you know it very well that there is a term that is solid angle. Solid angle is a three-dimensional equivalent angle, three-dimensional equivalent angle to an ordinary two-dimensional plane angle, to an ordinary two-dimensional plane angle. Okay, you can see the spreading out of light. You can see the spreading out of light. You know it very well that light is spreading in all direction, that has spherical nature, so you cannot find out the angle between the or among the spreading parameter, that is x, y, and z by theta. You have to define it by another angle, that is solid angle. Solid angle is defined here. Solid angle, its unit is steradian. Let us suppose this is our direction of spreading of light. So this is the area vector, and it's, since it is area vector, so it has an unit vector that it must have direction, and this is the direction. It is defined by n cap, and we are taking the solid angle over ds, that is small area. Solid angle subtended by area element bs at the center of O of a sphere of radius r. and it is written mathematically d phi is equal to ds cos of theta over r square. So phi is equal to integration of d phi, and we are getting integration of ds cos of theta over r square is equal to 4 pi steradian. Gauss theorem. Let's see the surface integral. Okay, the surface integral of total electric field intensity, the surface integral of electric field intensity over any closed hypothetical surface. This hypothetical surface is called Gaussian surface. This hypothetical surface is called Gaussian surface, is in free space is equal to 1 by epsilon naught times of the net charge that is enclosed within this surface. That is enclosed within this surface. Okay. So phi is equal to integration, that is closed integration E dot ds is equal to 1 divided by epsilon naught summation of I is equal to 1 to n in q1, because this enclosed surface having numerous number of charges. That's why I have written here pi is equal to 1 over epsilon naught into summation of qi, sum of qi, sum of qi. Okay. Okay, this is the proof of Gauss theorem. Let's see. This is the spherical symmetric surface, and its center is O. Here, Q, that is plus Q charge, is placed at the center of this spherical symmetric surface. Now, this is the small area that is ds, and its direction along the E naught, sorry, E. Here, the direction of electric field intensity and the direction of area vector, that is ds, is same. So E ds is equal to 1 divided by 4 pi epsilon naught q by r square, and this is the vector form. This is the vector form of electric field intensity. That's why I r cap is multiplied here dot ds n cap. D phi is equal to 1 over 4 pi epsilon naught q ds over r square. Now this is our concern to find out what will be r dot n. Since the direction of r and n are aligned, so angle between these will be 0. Now we are getting this value is equal to 1. So this is our equation, that is d phi is equal to 1 divided by 4 pi epsilon naught q ds r square, q ds r square. Now if you want to get total flux, so you have to integrate this. After integration, we are getting this value 1 over 4 pi epsilon naught q by r square into 4 pi r square, and this is 1 divided by epsilon naught into q, that is 1 by epsilon naught times of q. This is our Gauss theorem. Let's see my next topic. Proof of Gauss law or theorem for a closed surface of any shape. Let's see this. This is our equation of flux, that is electric flux, and here r cap dot n cap is equal to cos of theta, because there is no definite value of theta. That's why I have written cos of theta. Now putting this value, this equation in this equation, q divided by 4 pi epsilon naught ds cos of theta by r square. Now after integration, we are getting this value. So phi, total phi is equal to q divided by epsilon naught. Okay. Deduction of Coulomb's law from Gauss law. Let's see, this is our spherically symmetrical surface. Here, this is our small area ds, and the direction of ds and E will be same. So here we can write pi of E is equal to Q divided by epsilon naught. Now integration of ds we can write from the integration of ds is equal to 4 pi r square, and let it becomes E into 4 pi r square is equal to Q divided by epsilon naught. Now this is our equation and it is similar to the Coulomb's law. Okay, my dear boys, Gauss law, it is very new theorem or a new addition into our syllabus. So no, don't be tensed about the boys. Don't be tensed about the application of Gauss law. Okay. Okay, my dear boys. Now I am going to discuss electric dipole. Let's see what is electric dipole. You know it very well that electric dipole is the separation of two equal and opposite charges. Two equal and opposite charges, and the product of each of the charges of the dipole and the separation or distance between the charges is called electric dipole moment. Let's see what is the electric dipole moment. Okay, dipole moment. Electric dipole is a pair of equal and opposite charges separated by a small distance. Okay, by a small distance. The electric field produced by a field is known as dipole field. Electric dipole moment is a vector quantity used to measure the strength of an electric dipole. Okay, boys, electric dipole moment is a vector quantity and it is being used to measure the strength of an electric dipole. But electric strength or electric field intensity is also a vector quantity, but it is being used to measure the strength of electric field. This is the difference between electric dipole moment and electric field intensity. Okay, this is the separation of two charges, and this is 2L, and this it was supposed to address these questions why we are using 2L. Yes, we are using 2L because the center of these two charges is O. From this O point, Q minus Q is located by L distance and plus Q is located by L distance. That's why we are using 2L. Okay. And the direction of electric dipole moment is minus to positive charge. Okay, and this is the equation for electric dipole moment. The magnitude of electric dipole moment is the product of magnitude of either charge and the distance between the two charges. The direction is from negative to positive that I have told a little bit ago. The SI unit of P is coulomb meter. Note, an ideal dipole is the dipole in which the charge becomes larger and larger and the separation becomes smaller and smaller. Okay, my dear boys, you have to remember that the separation between these two charges should be smaller to smaller, and the value of charge should be larger to larger. Okay, for making an ideal dipole, for making an ideal electric dipole, for making an ideal electric dipole. Okay, Electric field intensity due to an electric dipole at first at a point on the axial line. Okay, this is the position of two charges and this is the direction of P, and the middle point of these two charges is O. We are going to determine electric dipole moment at point P, that is x distance away from O, that is x distance away from O. Okay, now we are going to determine the direction of electric field intensity at point A for point A, at point P for A, and at point P for B. Okay, the direction of electric field B is like that, and electric field EA is like that. Okay, so it is very much clear to us that the direction of two electric field intensity is opposite to each other. And you know it very well that resultant electric field, that is EP is equal to A plus EB, and we have a equation that is EP or R is equal to the resultant vector R is equal to root over P square plus Q square plus 2PQ cos alpha. Hence, it is the case of 180. That's why we or I can write very easily the form of equation, that is EB minus EA. EB minus EA. This is our equation, but the angle between these two position is 180. That's why it becomes EB minus EA. After putting this value, it becomes EA is equal to 1 divided by 4 pi epsilon naught Q divided by X plus L whole square into unit vector. And similarly, EB 1 divided by 4 pi epsilon naught Q by X minus L is square into unit vector. Unit vector I is written here because this coaxial point along the x-axis, and along the x-axis unit vector is I cap. Now total electric field E is equal to 1 divided by 4 pi epsilon naught Q divided by X minus L whole square minus P divided by X plus L whole square. After the calculation we are getting our electric field intensity, that is EP is equal to 1 over 4 pi epsilon naught 2 px divided by x square minus L square whole square. EP is now like that, but there is a condition. If L is very less than x, L is very less than x, then what will be happen? This L is very less than x, then what will be happen? Yes, let's see. EP is equal to 2p divided by 4 pi epsilon naught x cube. 4 pi epsilon naught x cube. The direction of electric field intensity at a point on the axial line due to a dipole is always along the direction of the dipole moment. Is always along the direction of dipole moment. Okay, let's see the corresponding electric potential for this coaxial line. Okay. At a point on the coaxial line, we are going to determine electric field for the dipole moment. Yes, it is our dipole moment. Now this is the separation, and we are going to determine electric potential at point A, and it is x distance away from O. Now resultant potential is Vp is equal to Va plus Vb. For minus q charge at point A, potential Va becomes 1 divided by 4 pi epsilon naught minus q divided by x plus L, and for P is equal to 1 divided, sorry, and for similarly VB also will be 1 divided by 4 pi epsilon naught plus Q divided by X plus L. Now we are getting our total electric field or electric potential, that is Vp is equal to Va plus Vb. After this calculation, we are getting Vp. After this calculation, we are getting Vp is equal to 1 divided by 4 pi epsilon naught P divided by x square minus L square. X square minus L square. If L is very less than X, then what will be happen? Obviously, Vp is equal to P divided by 4 pi epsilon naught X square, 4 pi epsilon naught X square. Okay, my dear boys, I have discussed about the electric potential at a point on the axial line, and it is the common equation that Vp is equal to 1 divided by 4 pi epsilon naught P divided by X square minus L square. Okay, my dear boys, now I am going to determine electric potential for the second case. At first, I will going to determine or discuss about electric field intensity for the second case, that is at a point on the equatorial line, that a point on the equatorial line. Okay, let's see. The equatorial line is Q, and it is x distance away from the point O, and it is also perpendicular distance from point O, and this is our line that is joined A and Q and B and Q through an angle theta. So at point Q, we will be determined the direction of electric field, that is E is outward from Q, and EA is inward from Q, and EQ is the resultant distance. Okay, let's see. Resultant electric field intensity is EQ is equal to EA plus EB. Now EA is equal to 1 divided by 4 pi epsilon naught Q divided by X square plus L square, and EB similarly. So here we are using our equation, that is the vector resolving method. Along this line, boys, along this line, the resultant electric field is acting. Okay, so we are getting two components along vertical and horizontal. Okay, vertical component EB sine of theta and horizontal component EB cos of theta. Okay, similarly for A, vertical component EA sine of theta and EA cos of theta. This is horizontal component of EA. Now the vector EA sine of theta, EB sine of theta are opposite to each other and hence cancel out. Obviously, the direction of these two vertical component are vice versa. So we will not follow this. The vectors EA cos of theta and EB cos of theta are acting along the same direction and hence add up. E cos of theta, EB cos of theta. After calculation, we are getting EQ is equal to EQ is equal to 1 divided by 4 pi epsilon naught Q to L over x square plus L square to the power 3 by 2. This is our main equation for the electric field intensity on the equatorial line for electric dipole. That is EQ is equal to 1 divided by 4 pi epsilon naught into P divided by x square plus L square to the power 3 by 2. And there are some special case for the determination of electric field intensity on equatorial line. Let's see what will be happen if L is very less than X. Yes, we are getting this equation for that case. This is very special case. If the observation point is very far away, then the electric field intensity at a point on the axial line is double the electric field intensity at a point on the equatorial line. Okay. If L is very less than X, L is very less than X, then EP will be twice times of EQ. EP will be twice times of EQ. Okay. Electric potential due to electric dipole at a point on the equatorial line. Boys, I am now discussing some special case for the determination of electric potential due to electric dipole. At first, at a point on the equatorial line, Vp will be 0, and at any point in an electric field, Vp will be Q divided by 4 pi epsilon naught P cos of theta x square. P cos of theta x square. Okay. Torque on an electric dipole in an uniform electric field. In an uniform electric field. My dear boys, you know it very well from your Newtonian mechanics chapter that torque is the product of force and perpendicular distance. Force and perpendicular distance from the acting point. Here, we are going to determine torque due to electric dipole. Okay, you can see that there are the separation of two charges, that is minus q and plus q, and the direction of torque is like that QE, and here QE, as the direction of this two torque as the direction of these two dipole moment is opposite to each other, so here is produced somewhat couple. Here is produced somewhat couple, and couple is the main factor to produce torque. Boys, torque means rotational force. Torque means rotational force. So let's see. However, the forces are along different lines of action and constitute a couple. Hence, the dipole will rotate and experience torque. Torque is the product of force and perpendicular distance. So, torque tau is equal to QE is multiplied by distance 2L sine of theta. We are using sine of theta because we are taking here the component. So that is PE sine theta. That is PE sine theta. Okay. Now torque is a scalar product. Sorry, torque is a vector product, and it becomes tau is equal to vector product of P cross E. And the direction of torque is perpendicular and into the plane containing the dipole moment, that is moment of electric dipole and electric field intensity. So SI unit of torque becomes Newton meter. SI unit of torque becomes Newton meter. Okay. We are now discussing about some special cases for torque. If theta is 0, then tau is equal to 0. If theta is equal to 90, then tau becomes PA, and it is the maximum value of torque in the electric field due to electric dipole moment. And cos theta and case 3 for 180 degree, cos theta for cos 180 degree, then tau is equal to 0, then tau is equal to 0. Okay. Okay, now my dear boys, we are going to discuss about the amount of work done due to torque in an electric field due to electric dipole moment. Let's see. Work done on electric dipole in uniform electric field in uniform electric field. When an electric dipole is placed in an uniform electric field, it experiences torque and tends to align in such a way that this dipole moment will regain equilibrium position. This is our dipole moment, and here this is electric dipole. Due to the electric dipole, the force Q is equal, sorry, F is equal to QE, F is equal to QE, and it also becomes torque, that is tau is equal to QE. Here, this electric dipole moment is deflected here somewhat angle, that is theta 2, and the difference between this theta 1 and theta 2 is d theta. So what will be our work? dw is equal to tau d theta. So tau is equal to PE sine of theta d theta, and we are going to integrate this from theta 1 to theta 2. Now we are getting PE cos of theta 1 minus cos of theta 2, and our potential energy due to this work done is U is equal to minus PE cos of theta, minus PE cos of theta. So now we are discussing some special case of potential energy due to electric dipole moment. If theta is equal to 0, then U is equal to minus QE. If theta is equal to 90, then U is equal to 0. And for 180 degree, U is equal to PE. Okay. U is equal to PE. Now, my dear boys, I think I have discussed elaborately about the electric dipole moment. Now we are going to see some mathematical problem on the basis of electric dipole moment. Let's see. An electric dipole placed in vacuum is formed by two equal and opposite charges of 2 microcoulomb and separated at a distance of 2 centimeter. Let's calculate electric field intensity at a point of 50 centimeter from the center located on the axis of the dipole, okay. Now we know it very well that calculate E at a point of 50 centimeter from the center located on the axis of dipole. We have an equation. Let's see this equation. Here the equation is EP is equal to 2p 1 divided by 2p divided by 4 pi epsilon naught x cube. Now for equation 1, we have to determine P is equal to Q2L. So we are getting somewhat value, that is 4 into 10 to the power minus 8 centimeter. Now it is very easy to calculate the electric field intensity located on the axial line. For B, calculate electric field intensity at a point of 50 centimeter from the center located from the center of the equatorial point. That is the perpendicular bisector. Okay. So perpendicular bisector or equilateral or equatorial point, that is our electric field intensity is equal to P divided by 4 pi epsilon naught x cube. P divided by 4 pi epsilon naught x cube. So P, the value of P is here, and x for X, this is 50 centimeter. Now it is very easy to find out the value of electric field intensity. So let's see number C. If the dipole is placed in the electric field of 2 into 10 to the power 6 Newton per Coulomb, 2 into 10 to the power 6 Newton per Coulomb, what will be the force? Boys, force F is equal to QE. Okay, F is equal to QE. Here, the value of E is like that and Q is also given here. So it is very easy to find out the force. Number D. It is very important question for us and it is also difficult. If the dipole is placed at an angle 30 in the electric field of 2 into 10 to the power 6 Newton per Coulomb and it will be deflected by 60-degree angle, then what will be the work? What will be the work? Boys, you know it very well that we are going to determine work done due to torque. Okay, due to torque, the work done becomes W is equal to PE cos of theta 1 minus theta 2. So P, it is very easy to determine P. It is very easy to determine P. P is equal to 2LQ. P is equal to 2LQ and E is given here, that is 2 into 10 to the power 6. So let's see what will be happen here. W is equal to P. P is equal to 2L into Q is multiplied by E and the difference of cos of theta 1 minus cos of theta 2. Okay. Now putting this value, you will get the result of work done. Okay. It is very easy to find out this value. Okay, my dear boys, I think I have covered up the total topics that is basis on my today's discussion. So no more today. Let's see my class. Yes, my dear boys, I have inserted here some sorts of question on the basis of my today's discussion. Let's see the knowledge based and comprehension based questions. This is the example of application based questions and higher order level questions. Let's see. There are some sample of MCQ. Let's see and try your level best to find out the answer of this MCQ questions. Okay, home task. This CQ is given here as your home task. You should try your level best to solve this CQ. If you face any problem, please tell me. I will here to solve your questions. And make 20 MCQ on the basis of my today's discussion and be sincere about your assignment on Thursday. My dear boys, at the very end of my today's discussion, I want to say, if you have any query, please ask me. If you have any query, please ask me. I will be here to solve your question, to answer your question. You know it very well that, my dear boys, we are passing very tough and rough situation due to COVID-19. So don't go outside of your home, stay safe, pass quality time with your parents and family members, be attentive with your online class and be punctual about your online assignment and try to follow this prevention, that is prevention tips about COVID-19. Thank you very much for attending my class, dear cadets.